Welcome again to this presentation. Today we are starting on question 16. Last time we ended on question 15. Question 16 is saying, what is the molarity of a dilute aqua solution of urea? We have urea. If the vapor pressure above the solution is 22.83 millimeter mercury, that means the vapor pressure of the solution was given. We have also the temperature as 25 degrees Celsius. Assume that the urea is non-volatile, then the vapor pressure of pure water is 23.77 millimeter mercury at 25 degrees Celsius. So that means we have the vapor pressure of the pure solvent, and also we have the vapor pressure of the solution. Now they are asking what is the molarity of the solution. Remember the formula that we use when we have the vapor pressure of the pure solvent and the vapor pressure of the solution, we can get the mole fraction of the solvent. Let's start to see on what do we have. What do we have in the question? We have here the vapor pressure of the solution, which is 22.83. It is here in the question. It was given the vapor pressure of the solution. What do we have again? We have also the vapor pressure of the pure solvent, which is 23.77 millimeter mercury. It was also given. And we know that the vapor pressure of the solution is equal to the vapor pressure of the pure solvent times the mole fraction of the pure solvent. And we also know that if you add the mole fraction of the pure solvent plus the mole fraction of the solid, you get 1. That means the mole fraction of the pure solvent is equal to 1 minus the mole fraction of the solid. If we can do the rearrangement, different rearrangement, you can see we are replacing this 1 minus b. We are replacing it here to replace the XA or the mole fraction of the pure solvent. In this case, we get this one. Then we can multiply this one with this one. We also multiply this one with this one. That is what we get. Then here we can push this one on the other side, p minus p0, which will be equal to this one. Then if we multiply the negative here and also multiply the negative here, we get P naught, or the vapor pressure of the pure solvent minus the vapor pressure of the solution, which is equal to this term. That means the vapor pressure of the solid, the mole fraction of the solid, will be equal to vapor pressure of the pure solvent minus the vapor pressure of the solution dividing with the vapor pressure of the pure solvent. So by using this formula, we can determine the mole fraction of the solid, and the solid that was given is the urea. Now we are looking at the molarity, and we know that this is the mole fraction of the solid. The mole fraction of the solid is equal to P, the vapor pressure of the pure solvent, minus the vapor pressure of the solution divided with the vapor pressure of the solvent. Let's see what is the molarity that they are asking. Remember, the molarity is equal to mole of solid dividing with kilogram of the solvent. That's what is the molarity. If we can change this mole into, what is this mole? This is the mass over the molar mass. Then we multiply this kilogram of the solvent, or the mass of the solvent in kilogram. That is another formula to calculate the molarity. Either you can calculate it by using mole of solid per kilogram of solution, or we can use the mass of the solid over the molar mass. This one, the mass of the solid over the molar mass, this is the number of mole, then times the kilogram of the solvent, which is here. This is what you have the molarity. Now the solution in the problem, they tell us that the solution is the very diluted solution. The solution is diluted. The solution is diluted. Then we have seen this term, which is equal to P naught minus P over P naught. That means the vapor pressure of the pure solvent minus the vapor pressure of the solution dividing with the vapor pressure of the pure solvent. That means that is the mole fraction of the solid expressed in terms of the vapor pressures. But we can also express in terms of mole. That means the mole fraction for the solid will be equal to the moles of solid dividing with the total moles. Total mole equal to mole of solid per C, mole of the solvent. Then for the rest of the solution, we know that the mole of solid are negligible, are very negligible as compared to the moles of solvent. That means this mole of solid can be negligible as compared to the moles of the solvent. That means for the rest of the solution, the XB or the mole fraction of the solid will be equal to the mole of solid over mole of the solvent because the mole of solid are negligible. But this is applied when you have a diluted solution, where you have the mole of solid negligible as compared to the mole of the solvent. That means we can get, if we can here replace the mass over molar mass, here also replace mass over the molar mass. That means you have the mass of the solid over molar mass of the solid. Here also you have the mass of the solvent over molar mass of the solvent. Then what is this one? If we can then multiply this one here, the reverse, that means it will be equal to mass of the solid over molar mass of the solid times the molar mass of the solvent over mass of the solvent. If you check what is this one, this one, you can see this one, that is the same as the molarity. You can see mass of the solid over molar mass of the solid times this mass of the solvent, that is equal to the molarity. Then that means the mole fraction of the solid will be equal to the molarity times the molar mass of the solvent. This term here that you can see, when the solution is diluted, this term that you can see, that term is equal to the molarity. That means the mole fraction of the solid is equal to molarity times the molar mass of the solvent. That means what will be the molarity? Because we are looking for the molarity, that means the molarity is equal to XB, or the mole fraction of the solid dividing with the molar mass of the solvent. Now we can get this XB, or the mole fraction of the solid, by using the vapor pressure, the formula I have shown before. Then the molar mass of the solvent, we have it. That means the molar mass of the solvent, we have it. Then we can determine the XB, which is the mole fraction of the solid. That means we use the vapor pressure of the solvent minus the vapor pressure of the solution dividing with the vapor pressure of the solvent, or the values you have them in the equation. Then we get 0.039. Then the molarity will be equal to vapor pressure will be equal to the mole fraction of the solid dividing with the molar mass of the solvent. The molar mass of the solvent, because the solvent you have the water, that means we are going to use 180 gram per mole, but we need to convert it to kilogram. That's why you can see it is 0.018 kilogram per mole. In this case, we get 2.2 mole per kilogram, or 2.2 molar solution. That was question 16, because they were asking to calculate the molarity. Question 17 is saying the vapor pressure of the pure benzene is 100 torr. That means the vapor pressure of the pure solvent. Calculate the vapor pressure of diluted solution containing 24 gram of manfor. That means we have the 24.6 gram of the solid. Then they are saying it will dissolve in 100 milliliters of benzene. That means the volume of benzene was given. The density of benzene is 0.877 gram per mole. That means with density, we can determine the mass of the solvent, or the mass of benzene. Let's see what do we have. We have the vapor pressure of the pure solvent, which is equal to 100 torr, because the pure solvent is benzene, and the vapor pressure was given. We have also the mass of the solid, which is equal to 24.6 gram, the mass of the solid. We have also the volume of the solvent and the density of the solvent. From volume of the solvent and density, we can determine the mass of the pure solvent. We take the volume times the density, then we get 87.7 gram. Then you have the molar mass of the solvent. The solvent is benzene. That means the molar mass is 78.1 gram per mole as the molar mass of benzene. We have also the molar mass of the solute, which is equal to 152.2 grams per mole, which means the molar mass of this can fall. Then we can determine the MMB, which is the molar mass that was asking. Calculate the vapor pressure of pure benzene. The vapor pressure, they are asking to calculate the vapor pressure of diluted solution. What do we have here? The molar mass of the solid, you have it, you can replace it here. What is the unknown that they are looking for? They ask to calculate the vapor pressure of the diluted solution. That means the vapor pressure of the solution, this is P. The P naught we have, the other terms we have, we need to replace all the value and find this P, that is the vapor pressure of the solution. That's what they are looking for. Let's see, we can replace and then we see that we need this P, that's the vapor pressure of the solution that we need to calculate. In this case, we can do different rearrangement. So you can multiply this one, we have multiplied this one, this one, and this one, then you get this value. Here also, we multiply this one with this one, we multiply this one with this one. So we get this one. Then we solve and we get this one again. So this is the mathematical rearrangement. Then at end, we get the vapor pressure of the solution, which is equal to 85.6 torr. The other step, they are just mathematical rearrangement to find the P or the vapor pressure of the solution that was asked. So we can continue on another question, the question 18. Question 18 is saying at 20 degrees Celsius, the vapor pressure of pure benzene is 78 grams per mole. The vapor pressure was given of pure benzene. And the vapor pressure of toluene was also given. It was not given. They are saying at the vapor pressure of pure benzene, the molar mass was given, the toluene also was given, and the vapor pressure is here. For the benzene is 22 mm mercury, and for toluene is 74 mm mercury. The vapor pressure of pure solvent, the two solvent was given, benzene and toluene. What's the total vapor pressure above solution containing 20 grams of benzene and 20 grams of toluene at 20 degrees Celsius? So that means here we are having the two solvents which are mixed together. Then the vapor pressure that they are going to contribute, it will be the sum of the vapor pressures. That means they're asking what's the vapor pressure of the resulting solution. If you mix two solvents, that means we need to look the vapor pressure for each of the solvents and then we add them. The vapor pressure that they will exert, it will be the sum of the vapor pressure of each of the solvent. Let's see what do we have. We have the total pressure is equal pressure of benzene in solution plus the pressure of toluene in solution. That means the total pressure, we need to take the pressure of benzene in solution plus the pressure of toluene in solution. So the molar of benzene, we have it. That is the mass dividing with the molar mass. We can also get the molar of toluene. That's the mass also dividing with the molar mass. Then you can look also the molar fraction of benzene. That means we take the mole of benzene dividing with the total mole. You can get also the molar fraction of toluene. That is equal to molar fraction of toluene dividing with the total mole. Then from this one, you can look the vapor pressure of the benzene and the vapor pressure of toluene by taking the pure vapor pressure of the pure benzene times the molar fraction, and we get 11.9 mm mercury. The vapor pressure of the toluene also will be equal to the vapor pressure of the pure toluene times the molar fraction of toluene. We also get this one. Then for the total vapor pressure, we need to add them. Then we get 45.9 mm mercury as the total pressure that they are asking. That was question 18. That means we calculate the pressure of the solution for each. For benzene, we calculate the pressure of the solution, the vapor pressure of the solution for toluene. Then we add them as the total pressure. Let's move to question 19. Question 19 is saying how many grams of the non-electrolyte sucrose for molar mass must be added to 450 grams of water, we have the pure solvent, which is 450 grams. And the molar mass, we know for water it is 18 grams per mole. They want to have the vapor pressure of 745 mm mercury at 100 degrees Celsius. They want to get this 745 mm mercury as the vapor pressure of the solution at 100 degrees Celsius. That means they are asking what is the solute, the mass of the solute, the mass of the sucrose that we need to add to the solvent, to water solvent, so that we can get this vapor pressure. Now let's see what do we have. So we need to rely on the formula for the vapor pressure. So we have this one. If you convert this one 745 in this case to this one, we convert it to, we get 0.98 atmosphere for this one, which means you have the vapor pressure of the solution, which will be equal to 0.98 atmosphere. Of course, this is because we have given the 100 degrees Celsius. So at 100 degrees Celsius, what is the vapor pressure of water? Because we don't have here the vapor pressure of the pure solvent, but they are saying at 100, we know that the solvent is water. Then what is the vapor pressure of the water at 100 degrees Celsius? That's why we have converted to atmosphere this one. We know that at 100 degrees Celsius, the vapor pressure of water, of pure water, is 1 atmosphere. So that's one here we are converting to atmosphere. At 100 degrees Celsius, the vapor pressure of water is 1 atmosphere. And you know the vapor pressure of the solution is equal to vapor pressure of the pure solvent, which is the 1 atmosphere times the mole fraction of the pure solvent. So that means the mole fraction is equal to P over P naught. The vapor pressure of the solution, which is equal to 0.98, dividing with the vapor pressure of the pure solvent, which is equal to 1 atmosphere. Then in the case, we get 0.98 as the mole fraction of the pure solvent. After getting the mole fraction of the pure solvent, you know that the mole fraction of the pure solvent is equal to mole of water dividing with the total mole, that means mole of water plus mole of sucrose. Then we know the moles of the water. We can take the mass of water divided with the molar mass. After getting 25 mole of water, this is the mole of water. Then here also the mole of water. XA, we have it. This is 0.98. Then we calculate the mole of sucrose, which is the mole of the solid. After getting the mole of solid, then we can calculate the mass of the solid. So we can replace 0.98. This is the moles of water. This is also the moles water. Then we look for the mole of sucrose. We get 0.51 mole of sucrose. Then after getting the number of mole for sucrose to determine the mass, we multiply with the molar mass. Then we get 174.42 gram as the mass of sucrose that we need to add to water to obtain the vapor pressure of 745 mm mercury. Let's move to question 20. Which is also the last question for us. Question 20 is saying the boiling point of water is 100 degrees Celsius. Calculate the boiling point elevation and the new boiling point of an aqueous solution made by dissolving 50 grams of ethylene glycol in 50 grams of water. The Kb is 0.513 degrees Celsius per mole Kelvin. Here again we know the formula for the change in temperature, which is the boiling point elevation, or the change in temperature will be equal to I times the Kb times the M. This is the I is the dissociation. That means this one is will not dissociate because we have ethylene glycol is an organic molecule, it will not dissociate. That means the I will be equal to 1. The Kb is given, this is 0.513 degrees Celsius. Now we know we don't have the molarity. What will be the molarity? It will be the mole of solid per kilogram of the solvent. So the solvent, you have it with 50 grams of water, and the solid also we have it 50 grams of water. We can convert it to mole so that we can get the mole. So we can get the mole of solid. We take the mass of solid dividing with the molar mass. We have also the molarity is equal to 0.0806 mole dividing with the kilogram of the solvent. That means here the 50 grams you have converted to kilogram because molarity is mole per kilogram. Then after getting the molarity, we can get the change in temperature. The change in temperature or the boiling point elevation when you are adding the solid to the solvent, it will increase the boiling point. You have the boiling point elevation and the freezing point depression. Here we need to calculate the boiling point elevation, which is dt. If the boiling point elevation here, it will be equal to this formula. We have this one, I is equal to 1. We have this one. Then we multiply with this one, which is the molarity. Then we get 8.26 degrees Celsius. So we know that the boiling point, the normal boiling point is water. That means the boiling point elevation, that means it will be equal to 100 degrees Celsius, which is the normal boiling point of water, plus this increase in temperature, 8.27 degrees Celsius. That will be the new boiling point. The new boiling point will be equal to 100 plus 8.27, which will be equal to 108.27 degrees Celsius. That will be the new boiling point for this solution.